Okay, in this lecture, I want to finish a little bit about inheritance and then talk about traits, type parameters, generics, and type constraints. So last lecture we talked about inheritance and how we can have a base class A and another class B, a derived class that extends A. And part of the usefulness of this is that A could be known to have a function, say, called foo, and B will also have that same function foo, although the implementation can change. And we talked about how when we upcast, right, I can have a function, say, call foo, that takes an A and just calls that A's foo function. And we can also pass any B's to call foo, since B is a type of A, right? That's the idea of a derived class is a type of or a version of the superclass, right? Typically, we think of it as like a less generic form. And what's nice about this is that call foo only sees the fact that the B is some kind of A, but when it calls its copy of foo, we actually call B's version, right? We don't call A's version, we call B's version. We see that in these returns, right? That when we call foo B, we get B's version of foo overriding A's version of foo. And this is typically what we want to happen. But sometimes you want to be able to access your parents' version of the function as well, right? You don't always want this override thing to happen. So the way to do that is to use this keyword super, right? So the idea, it's pretty straightforward. We can still have class A and class B that extends A. We override foo, and we can call super.foo, and that will call whatever our parents' class version of foo is. Right, so this is just an easy way to access our immediate parents' content. And you see that this works as expected, right? I make a new B, I call it b.foo, and it runs super.foo followed by this print line. And what's the super.foo? Well, that's class A's version of foo, which just prints from A, whatever. So this is a nice way to handle this, and it works and is unambiguous because Scala only has single inheritance, right? So super only refers to one thing, since B can only extend one class. But often we want to be able to extend from multiple classes, right? C++ has multiple inheritance, and other languages do as well. And we don't want to get rid of that because, sometimes we recognize that an object is more than one thing, right? A car can both be a type of transportation as well as perhaps a type of house, right? We have multiple things that something can be, and we might want to extend from that. So how do we deal with having multiple extensions? And Scala does that with traits, which we've seen dealing with non-terminals in our abstract grammars. Right, we've been using traits a bunch, but they're essentially abstract classes that can have its own members and methods, right? So unlike the abstract class that we saw last time, we can actually give full definitions inside of our traits. And then we can inherit just like normal inheritance, we can inherit traits and classes. So for instance, I have a trait philosophical with a function philosophize, as well as a trait green with a function called color. And down here we make a class, frog, who has a name and extends philosophical. Right, and we'll make this get name and override toString. And then we can make some frogs and we can ask them to philosophize, and they do. So that's cool. We can't instantiate any traits themselves because they're considered abstract, right? So this doesn't work. But that's not what we want them for, right? If we wanted to do that, we would just do a normal class. There is a way to do this, but you should read that up on your own. So where are traits useful in programming? Well, here's a couple examples, right? Here's one where the idea is that we might want to change how we print depending on whether we've set a debug flag or not. So we can make this trait debug printer, right? And debug will be a flag that says, am I going to print with my debug on or not? And a debug print. So then in my class could extend debug printer, and I always just use debug print to print everything. And I can basically switch on or off whether I get my debug feedback or not, right? Just by changing debug to true or false. So it's an easy way to sort of group all of that debugging concepts together into one thing called debug printer. So here's another example that's a little more complex perhaps. Here we have our trait called an ordering. It's going to take in this bracket T. So this is this will work for a generic type T, which we can define later. And the idea here is that I want to have this function definition compare. Right, it's going to take in a T, and my whatever this trait, whatever extends this trait or mixes in this trait, should be of type T. And I'll be able to compare my current object with another object and return an int. And we'll get returns 0 if they're equal and greater than or less than, depending on if it's greater than or less than T. And then we can instantly overwrite all of these operators so that we can have greater than or less than directly with our objects, even though we've only defined this compare. And then we could do something like a sort list, where we have a list of these objects and we can just sort it with quicksort or whatever because we have less than or equal to already defined, right? Because that's all that's really necessary to do any sorts, is just having a definition of a less than or equal to. And a basic compare function does that. I've blocked out this equal sign because it gives a weird Scala error that I don't need to deal with right now. But let's see how this works in general. All right, so here we have a class A that's going to take in an X and a Y and extends an ordering of A's. Right, and so then all I have to do is write this compare A, and this will let me do things like this, right? I can say A, B, C, and then I can compare them. And we can see that A is less than B, A is not less than C, A is less than or equal to itself, right? All of these things are true, except A is not less than C. You can't put any parameters into a trait, right? No class parameters like this, since traits can't be instantiated themselves, right? And the only reason we would have class parameters is if we wanted to make objects of this thing, right? So traits are just about the body of functions and variables or values. For instance, to do this correctly, we just add color into the body. Right, and it still works just as expected. It's just that it doesn't have that syntax for being able to instantiate a color. And the reason why we also want to use traits is because we can mix in multiple traits. So we can't inherit from multiple classes, but we can mix in multiple traits. So here we have an abstract class animal, and we're going to make a class called a green frog, right? It has a name, it extends an animal, and then uses this keyword with for mixing in traits. So the with only works with traits, but philosophical and color are both traits. So we can mix in philosophical and color, and we can override philosophize if we want. We can change its color, right? And then we can see that this all works as expected. You can even do multiple colored frog, right, by adding this trait color here outside of, and also another color string here. And traits can also extend other traits or classes. Right, the trickiest thing here is whether or not you can extend something with a trait that extends from something else. Right, so we can only mix in a trait if that inherits from class A, if that class also inherits from class A. So we saw this type parameter in the ordering example. Right, so what is this bracket T? And we've also seen this a little bit in previous homeworks and lectures, or we sort of said just go with it, right? But let's look a little. Let's look into more detail as to what's actually going on here. The idea here is that I might not know what the trait or what the type I want to be dealing with is, but I want to be able to use that type in my code, right? So by putting the square brackets t, it says that I know that there's going to be some kind of type t that I'm going to be using throughout this. And once I do that, I can then start using this trait or type t throughout my code. And we see this particularly with stuff like lists, right? We saw this every time we see like a list and then in square brackets int saying that this is a list of integers. This is exactly what's going on here, right? The list has a bunch of different functions and data that are just of generic type t until we say, oh, t is an int, at which point everything is instantiated into ints. But it lets us be able to make a generic list class and then make a list of ints and a list of strings and a list of other things just by replacing t with a different type or different class. So we can see this in play here. Let's see, C does not take in type parameters. Oh, I need to run this first. There we go. Right, so I have this class C with a bracket T, and if I say let's do a class D, it extends C, but only for ints. Right, so we need to say what T is. T is some kind of capital T, which in this case is an int, so I'll put 42 there. I'm going to need to override, make my own definition of transform from my abstract class. And so I know what t is. In this case, it's an integer, so I can just basically transform it to 42. Right. We can also keep the generic aspect here. Right. I don't need to specify. I can just say that class E of bracket t extends C of t. Right. So I don't have to specify it, even if I'm inheriting it. When I do this, right, new E of hello, this is kind of interesting because, right, it binds hello to T here, which Scala automatically figures out, oh, that means that capital T is of type string. So little e is going to be of type E bracket string. Just like you can make a list of numbers and Scala will instantly figure out that it's a list of ints. Right, and same here, right? So f is a new e that's a list of strings, and so its value is going to be e of list of string. And you might have something complex, and Scala might not be able to do the type inference automatically for you, but that's pretty easy to just write. Right, we can always type in here that it's going to be e list of string, right? And just tell Scala what it's going to be. And yeah, so and we can even have a new class f, and then we can make e of f, right? So it doesn't have to be the built-in types. It could be any class, or I think traits work as well. But yeah, it gives you a lot of flexibility. So yeah, what happened here, right? So we have this call foo that's going to take in any possible t, and take an arg, and it's just going to call arg.foo. Ooh, that's right. That seems like maybe it should work, but we seem to have gotten this compilation error. What is the problem? Well, not every t in the entire type hierarchy of Scala has a foo function, right? So we don't actually know that this is a well-defined function definition, right? We might want to say call foo on string, and string doesn't have a foo function. So we don't want to be able to do this, but we might want to do this, but limited to the things that actually have foo. So how can we do that, right? How can we leave this generic, but still say that, well, this should work for anything that has a foo in it? So what we can do is we can do these type constraints. So we have a trait A, and it's defined to have this foo function. And then we say call foo with this little less than or equal to colon. And what it says is that T should be a derived class of A, or it should extend A, right? So you think of the less than or equal to as it's like below A, it is a type of A. And since A has foo, right, and if the only T's we allow call foo to implement with, right, is stuff that inherits from A, then this will work just fine. Right. Likewise, we can say make our class C that extends A, right? That's something of type T that extends A. This is exactly the same concept. And yeah, we can make a new C and then call foo on C, and this works as expected. Let's check out this next example, right? We have A, we have abstract B that extends A, right? That's where we define the foo. And then we'll call foo on anything that is a subclass of B, right? Since B is the thing that has foo, we should be able to do this, right? And then we'll have class C extends B, and that will just overwrite whatever foo, right? We didn't define what foo does here, but we'll define it down here. And we can call foo on a new C. So we can see that we don't have to say leave that at the highest level, right? We can basically tighten down our type constraints to exactly where we need them to be. And for instance, we can't call foo on A since A is a superclass of B, and we said that all types that call foo can be used on have to be subclasses of B. So this is where the class hierarchy, the type hierarchy, really comes into play, and we can see how we can basically allow for as much generic action as we want. We can also do the opposite, right? So we can have a situation where we might want to only do things that are larger, right? So let's see, let's go through here, right? We have a trait of a thing, we have a vehicle that extends a thing, we have a class car that extends vehicle, we have a class bus that extends vehicle, we have a class sedan which extends car, we have a big car that extends sedan, we have a Jeep that extends big car, motorcycle that extends vehicle, and a tomato that extends thing. Right. So what would be useful, I recommend doing, is just drawing out what is the tree of this whole thing. And then we could do this, right? We could say parked vehicle of A, right? And we could see what do we have here. So A is just going to be a placeholder. Oh yeah, we can't do this, right? Because there's no name in our type A. We defined class A a while ago. And in general, A, if it's generic, right, we don't have to put T there. We could put really any name that's not bound. We already bound A here, but we could do something like S. And we still have the same issues, which is that not everything has a name. But we know that everything that is a subset of a thing, right, we said thing has this name. So everything that we've defined in here has a name. So yeah, we want to make sure to only talk about parking vehicles for things, right? Because we want to be able to use its name. And so we can make a new parked vehicle on a new sedan, and it just gives us the name back, right? But we can also do it on a tomato. Right, so maybe making sure that everything that is less than thing is sort of too wide, right? Park a bus. So how do we add that constraint? Well, we could say we only want to park things that are less than, right, that are cars or smaller. And then, well, we can no longer park a bus, right, because a bus was not a car. You can also no longer park a tomato, so that's good. But we can also bracket things on both sides, right? So instead of just bracketing from the top, we can bracket from the bottom as well. Since we said a big car is a type of car, right? So we can have we basically say A has to be above a big car, but less than a car. Right? That's what this type constraint is saying. And you can really read these directly as greater than or less than in terms of our type hierarchy. And now we could try to run this. Well, what was a Jeep, right? A Jeep was a type of big car. So we can't park that, right? Because A has to be, cannot be a big car or something that inherits from a big car. But we can park a sedan, right? We can, right? Why did this work? We were able to um, upcast our Jeep into a sedan, right? A big car is a type of sedan. That's what we have up in our hierarchy here. Right? Sedan extends car extends sedan, Jeep extends big car. So when we pass just a Jeep, we don't allow it to park, right? But if we upcast to sedan, then we can. And likewise, we can do the same thing here, right? So we can just instantiate a sedan, which we'll call as a Toyota, and then park the vehicle there. So this is a nice way to basically, once you've created your type hierarchy or your class hierarchy, how do you actually limit Liskov substitution principle, as it were, to make sure that you allow for the most generic functions possible while still maintaining the consistency of your type hierarchy.